Welcome to the AI checkpoints. The world of AI is just, well, moving at lightning speed, isn't it? And for those of us trying to keep pace, information overload is definitely a real challenge. We've certainly talked about retrieval augmented generation or RAG before. It's been such a game changer for grounding large language models, preventing those weird hallucinations. But what happens when standard RAG, the kind built on simple vector search, just can't keep up when it hits a wall with complex real-world data?
Well, that's what we're diving into today. It's an evolution that's making LLMs smarter, definitely more accurate, and far less prone to making things up. We're talking about GraphRag. This isn't just about finding similar stuff anymore. It's about leveraging the true power of relationships and context deep within your data. It's really about elevating AI's understanding.
That's it exactly. Think about it like this, right? Your brain doesn't just store facts in some kind of flat list. It connects them. It's this huge, intricate web concepts, people, places, events, all linked. And from the fantastic sources we've looked at from experts at NVIDIA, Neo4j, Harvey, Lance, and Ryder, that's precisely what GraphRag aims to do with your data. So our mission today is to unpack why GraphRag is becoming so essential in the AI toolkit, how it actually works, and what practical insights you can maybe take away to supercharge your own AI applications. Okay, so to really get why GraphRag is a leap forward, let's quickly touch base on the foundations again. Most of us are pretty familiar with standard RAG and its reliance on vector databases, yeah. Take your documents, chop them into chunks, turn those chunks into numerical vectors, and then find similar vector chunks when a user asks something. Sounds simple enough.
It does sound simple, and look, it's definitely a great starting point for a lot of things. But as Stephen Shin, writing for Neo4j, points out, these basic RG systems often fall short. They pull back just a fraction of information based purely on that vector similarity. And maybe surprisingly, that's not always the same as actual relevance to what the user is really asking, especially if the question is complex.
Right, and that's where things start to get, well, tricky. Sam Julian from Writer, for instance, he puts it quite bluntly. He says vector search alone is insufficient for sophisticated retrieval at scale. That's pretty strong. He even mentions Joe Christian Bergham's article about the rise and fall of the vector database infrastructure category, suggesting the whole industry is kind of waking up to this limitation.
It is a bold claim, especially given how central vector databases have been. And what's really compelling is how this basic vector retrieval can actually lead to wrong answers, particularly with what's called naive chunking, just, blindly cutting text up. Sam Julian gives this brilliant example about Apple's founding history. Imagine if Macintosh 1984 and Lisa 1983 accidentally land in the same text chunk. A simple nearest neighbor search might tell you the Mac came out in '83. It completely loses that critical temporal relationship. The sequence, the order, it's just gone.
Exactly. It misses the obvious connection. And it gets even messier with what Sam Julian calls concentrated data. Picture a mobile phone company with thousands of documents, all talking constantly about megapixels and battery life, very similar language everywhere. If you ask for a comparison, a simple vector search really struggles because, well, everything looks the same vector-wise. It's genuinely like trying to find one specific needle in a haystack made entirely of very similar needles. You just get more needles back. It really shows the nuance we lose. Spot on. And there's more. Stephen Shin also explains that while these traditional vector databases might seem easy to start with, they aren't always robust or mature enough for, say, enterprise-grade scale. And crucially, they often lack explainability. It's really hard to figure out why a certain result popped up. Plus, you still got the underlying LLM risks, hallucinations, data bias if they're not properly grounded. Basic vector search doesn't fully solve that grounding problem.
So, okay, given all these limitations with just looking at similarity, it's pretty clear we need something more sophisticated, and that's exactly where GraphRag comes in. It feels like it fundamentally changes how LLMs access and, maybe more importantly, interpret information. It's all about bringing structure and critically context into the picture, giving the LM a much richer map of the data. Absolutely. Michael Hunga and Stephen Shin both describe a knowledge graph pretty straightforwardly. It's a collection of nodes, relationships, and properties, entities linked together. It's really about explicitly showing the connections between things, people, places, concepts, events, you name it. Mitesh Patel from NVIDIA really stresses the importance of this edge of relationship. That connection itself isn't just a line, it's data. It carries meaning.
Okay, so instead of the system just seeing ExxonMobil and spending as maybe related keywords in a chunk, a knowledge graph could explicitly show ExxonMobil cut spending on oil and gas exploration. That verb, cut, that's the relationship, right? It defines the interaction.
Precisely.
Yeah.
That's the core idea. It lets GraphRag capture the information between entities in much, much greater detail. It provides a far more comprehensive, more nuanced view of the knowledge landscape. Stephen Shin uses this really great analogy comparing it to the human brain. He suggests the logical, fact-reasoning left brain is like the knowledge graph, and it enriches the creative, pattern-recognizing right brain of the LLM. So it's about grounding the LLM's creativity with hard facts and their explicit links, making sure it thinks more logically, you could say.
I love that analogy. It really clicks. Grounding creativity with concrete, verifiable connections. And this context-rich approach means, well, better relevancy, answers you can actually explain, and even the ability to layer in things like security and role-based access control. Stephen Shin also mentioned a Microsoft research paper showing GraphRag can sometimes get better results with less token costs. That's huge for efficiency, right? Using fewer language chunks to get the answer.
Definitely a big win. And the real-world impact is already pretty clear. LinkedIn, for example, used knowledge graphs to improve their customer support significantly.
Yeah.
They cut the median time to resolve issues by nearly 29%. That's a massive operational gain. And a Data.World study showed a 3 times improvement in LL or response accuracy comparing RIGs on SQL versus graph databases. Plus, if you look at Gartner reports, GraphRag is consistently trending up. It's seen as a key tech breathing new life into the whole AI ecosystem. It's definitely got momentum.
Okay, this sounds incredibly powerful, but, the practical side. How do you actually build one of these intelligence systems? It sounds complex.
It can be. But Mitesh Patel from NVIDIA breaks it down into maybe 4 high-level components. First, you've got your raw data, then data processing. Third is the graph creation itself, sometimes called semantic embedding if you're doing a hybrid thing. And finally, inferencing, asking questions, getting answers.
Michael Hamunga from Neo4j also talks about 2 main phases, right? The knowledge graph construction and then the search part.
Exactly. And that construction phase is absolutely critical.
Yeah.
The quality and richness of your knowledge graph directly dictates how good your retrieval will be. Get that wrong. And everything downstream suffers. It's the foundation.
So it sounds like the first massive hurdle is taking all that unstructured stuff, articles, emails, notes, whatever, and turning it into those structured triplets. Subject, predicate, object, like ExxonMobil cut spending. Mitesh Patel actually warns this is where you might spend like 80% of your time, just iterating, refining, getting the ontology. That's your defined structure of entities and relationships, getting that just right.
He basically says if your ontology or the triplets you extract are noisy or inaccurate, your retrieval results will be noisy too. Makes sense. That's where the hard work often is.
Yeah, that sounds like where the magic or maybe the frustration happens.
It really can be. But as Michael Hamunga points out, LLMs are actually pretty good at this extraction part now. They understand multiple languages. They're flexible, especially with these massive context windows they have now. You can even feed them existing ground truth data examples of good entities and relationships to sort of guide their recognition and make the extraction more accurate for your specific needs.
Okay, so once you've built this hopefully robust knowledge graph, then the retrieval part kicks in. Mitesh Patel really emphasizes the importance of multiple hops in the graph here. You're not just doing a single flat lookup. It's about following chains of relationships, right? Moving from one node across a connection to another node, maybe multiple times, to gather much richer, deeper context for the LLM. It's like tracing a line of reasoning.
Exactly. But there's always a trade-off, isn't there? The deeper you hop, the better, more nuanced context you get, potentially. But latency, the time it takes to get an answer, becomes a real factor. Users expect speed. Mitesh Patel mentions NVIDIA's QGraph library here, which uses GPUs, powerful hardware, to speed up these complex graph searches significantly. It allows for that deeper exploration of relationships, but with much less waiting time, helping find that balance between depth and speed.
Makes sense. And critically, how do you know if it's all actually working well? Evaluation must be key.
Oh, absolutely. Calvin Chee from Harvey puts it perfectly. Evil-driven development is a huge, huge key. He explains there's no single magic bullet for evaluation. You really need a range of methods. You might need costly expert reviews for that gold standard accuracy check, but also faster automated metrics like retrieval precision and recall for, quicker feedback loops during development.
Mitesh Patel also talked about evaluation tools, didn't he? Like Ragus.
Yes, Ragus. He mentioned it's a simple pip install library, which is nice. It's designed to assess your entire RAG pipeline, from the query itself through retrieval to the final LLM response. It uses metrics like faithfulness, answer relevancy, coherence, helps you see the whole picture. They even trained a specialized reward model at NVIDIA, Lanotron 340M, specifically to judge the quality of LLM responses, which gives a more objective assessment.
Okay, so theory is one thing, but putting this into practice, especially for big enterprise-grade systems, that must bring its own set of fascinating challenges. Calvin Shi from Harvey and Chang Shi from Lance shared some really eye-opening stuff from the legal world, didn't they?
They really did. I mean, just imagine the data scales they deal with. Often tens of millions of documents. And these aren't simple documents either. They're super long, incredibly dense, packed with highly specific legal language. And the queries, Calvin Key gave that example, they're fantastically complex. They involve subtle semantics, implicit filters, specialized data sets, tons of domain jargon.
Oh yeah, that legal query example was a real mouthful. What is the applicable regime to covered bonds issued before 9 July 2022 under the Directive EU 2019-2062 and Article 129 of the CR?
Wow. Just trying to parse that requires precision, let alone finding the right answer accurately without something like a knowledge graph.
Exactly. And beyond just the complexity of the queries, data security and privacy are absolutely paramount, especially in regulated fields like law or finance. This means you need meticulous ways to segregate data, ensure only authorized people see certain things, and strictly adhere to data retention policies. It adds another layer of complexity.
So what kind of tech stack can actually handle all of that? The scale, the complexity, the security?
Well, Changshi introduced LanceDB. They call it an AI-native multimodal lakehouse. It sounds like it's basically a unified platform built specifically for the messy reality of AI, data, text, images, audio, embeddings, tabular data, all of it. It's designed for massive scale, leverages GPUs for super fast indexing. He mentioned indexing billions of vectors in hours, which is incredible, and it separates compute from storage, which helps manage costs. And what's unique about it?
The key thing Chang-Shi highlighted is its ability to store all that diverse AI data in a single table structure using their open source Lance format. This acts as a single source of truth. It avoids having multiple copies of data scattered around and the nightmare of keeping them all in sync, which is a huge pain point for AI teams. Streamlines things a lot.
Interesting. And Writer, another big player, they also hit scaling walls, right?
Yeah, Sam Julian shared their journey. They initially struggled with efficiently converting their data into graph structures. And then they ran into the cost and the specialized expertise needed for traditional graph databases. It shows that even the leading companies iterate and have to find clever workarounds.
So what was their workaround?
It was pretty smart, actually. They built a specialized, smaller AI model whose only job was to map their data into graph structures. Then, instead of pouring that into a dedicated graph database, they stored the resulting graph data as JSON just structured text inside a Lucene-based search engine.
Lucene, like what powers Elasticsearch and Solr?
Exactly. It leveraged their team's existing skills with search tech and scaled efficiently for them without needing a whole new database system or specialized graph expertise. Very pragmatic.
Okay, now this next bit from Sam Julian at Writer really caught my ear, their breakthrough with something called Fusion and Decoder. He described it as building on the original RAG idea, but without feeding all the retrieved context directly into the LLM's prompt. Sounds counterintuitive, almost.
It is a really interesting twist. They adapted this concept specifically for knowledge graphs. So, knowledge graph with fusion in decoder, as they call it. It processes the relevant passages or graph snippets independently first, which scales nicely. Then it aggregates the evidence from those pieces jointly, but later in the process, inside the decoder part of the LLM. He claimed this significantly drove down their hallucination rate and boosted efficiency.
And they had proof.
Apparently so. Their internal benchmarks showed their system achieved the best accuracy and the fastest response times compared to 7 different vector search systems they tested against. That's a pretty strong endorsement for their approach.
Wow. Okay, so after hearing all this incredible innovation and the different approaches, we land at the million-dollar question for you, our listener. Should you go full graph RAG? Should you stick with semantic vector RAG? Or maybe try some kind of hybrid? Mitesh Patel gave us the classic wise answer, didn't he?
He did. It depends, which is often the truth in tech. He suggested focusing on 2 main things. First, look at your data. If you have traditionally structured data, think of retail inventories, financial transactions, employee databases, those are often excellent fits for graph systems. The relationships are already quite explicit. Even with unstructured data, if you find you can extract a good, meaningful knowledge graph from it, then it's definitely worth experimenting. But the quality of that extracted graph is key.
Right, that 80% effort thing again. And the second factor?
Your application and your specific use case. Ask yourself, does my use case truly require understanding complex relationships to get the right answer? Do I need to infer connections? Does accuracy depend heavily on context beyond just keywords? If yes, then GraphRag probably makes a lot of sense.
But otherwise, remember, these can be compute-heavy systems. So the benefits really need to justify the added complexity and resource cost compared to simpler vector ARIA.
I think the main takeaway, listening to all these experts, is that there isn't just one way to get the benefits of knowledge graphs into your RAG system. Whether it's using a dedicated graph database like Neo4j, or a clever approach with search engines like Writer, or these advanced techniques like Fusion and Takecoder, or platforms like LanceDB, the core principle is fundamentally about intelligently leveraging the relationships that are already present, but often hidden in your data. It's not just about the text itself.
That's a great way to put it. So the ultimate takeaway for you listening might be this. If your AI system is struggling with accuracy or nuance or explainability, don't just think about adding more data. Maybe challenge your assumptions about how that data is connected or could be connected. GraphRag's real power seems to lie in revealing those hidden relationships, turning that potential information overload into genuinely intelligent insight. What a fascinating deep dive into the world of GraphRag. It really feels like understanding these connections is the next big step for supercharging AI.
I agree. The insights from Mitesh Patel, Stephen Shin, Michael Hunga, Calvin Chi, Chang Shea, and Sam Julian all really point in the same direction. While vector search definitely has its place and got us started, the future of truly intelligent, reliable, and frankly trustworthy AI systems seems to lie in embracing the rich, contextual power that knowledge graphs offer.
So for you, our listener, maybe the next time you're working with AI, ask yourself, what crucial relationships might I be missing in my data right now? How could connecting those dots unlock even more powerful, more precise, and hopefully less creative insights from my LLM? We really hope you enjoyed this deep dive. Hit like and subscribe if you like the content. See you next time.